Hey, hi everyone, welcome to another ALP video. This one's on geometric probability and 3D geometry. So 3D geometry is sometimes a scary topic, but there's just a few tips to doing 3D geometry problems. The first one is try to draw pictures from many angles because that sometimes helps a lot. Like if you have a weird cone or something, then draw like a cross section which might look like this, and draw like maybe a section from the bottom, like a circular cross section if that helps. Just like draw lots of pictures and stuff. Okay, so first of all, I'll just write down like a few commonly used formulas for like volumes and stuff. So for like pyramids, tetrahedrons, cones, all of those things, it's basically just height times base divided by 3. So this one's really common. That's a multiplying sign over 3. You probably know this already, but this is the most common one. And yeah, so, okay, we're gonna start with a problem that's kind of combinatorial, well, more probability, but yeah. So this problem is, what is the probability that when 3 numbers are chosen from the interval 0 through 1, that their sum is less than 1? So, I mean, you could try doing this by keeping one number constant, like saying that, what if one of the numbers was 0.5, and then you only have 2 variables to worry about, and that's easier. But the problem is that there's the numbers they don't have to be integers, so they can be all sorts of decimals, and there's an infinite possible number of values they could be, like 0.499, etc. So it really helps to use geometric probability in this case. And since there's 3 variables, it might help to draw a cube, since we usually draw squares for geometric probability, or rectangles. But since this is 3D, we might as well draw a cube. So, okay, here's our cube. And actually, this cube contains all the possible triples x, y, and z, if we call it x, y, z. Because we can say that this is 0, 0, 0, and then this one is 1, 1, 1, and then maybe this is 1, 0, 0, and this is 0, 1, 0, something like that. So yeah, let me draw these vertices too, because these are important. Okay. So yeah, this cube contains all possible triples x, y, and z. Now, all we want to know is how many of these triples work. And then we just need to find the ratio of the volume of triples that work to the total volume. Let me erase this for a second. Okay, that's good. Now, since this is an inequality, the best thing that we can do first is calculate the equality case, when the sum equals 1. because then we can find like the boundary, and then everything to one side of the boundary will work and everything to the other side will not work. So let's start by looking at some numbers, some points that do work, or that are on the boundary, so their sum is 1. Well, obviously these 2 points work because 0, 1, and 0, 1, 0, 0. And then this one back here also works because, here, let me write the triple. It's 0, 0, 1, so that works. And then, okay, so there's something you may also notice. All the numbers on this line work because it's almost as if you do not have to care about the z variable on this one face that is colored in yellow because z is 0. So you just care about x and y. And obviously along that yellow line, this line, they all work. Similarly, along this line, back there on that back face, they also all work. And same for here. So you may be wondering if everything in this yellow triangle works. And it actually does, because here we basically just have the equation x plus y plus z equals 1. And whenever it's like a linear equation, so like there's no squares or cubes or anything, it's like always going to be linear. Like the graph is going to be flat. It's not going to be like, it's not going to be quadratic or anything. So in fact, all the points here are on the boundary, or like they're the equality case. This is the set of all points for which x plus y plus z is equal to 1, which means that everything on one side of that yellow plane will work. In fact, that's everything like below it, because x, y, and z are below the equality case, and everything above it in purple does not work. So in fact, the answer to this problem is simply the ratio of the area of this tetrahedron to the area of the entire cube. That tetrahedron, by the way, is this tetrahedron right here, formed by those three like edges, and then these 3 yellow edges. So this tetrahedron. And using the formula that we saw before about how tetrahedron volume, stick with red, is height times base over 3, we can easily find the area of this one because these are right angles. So it's just that the height is 1, the base is 1, and wait, no, the base is half. Yeah, the base should be half because it's a right triangle with like 1, 1, and root 2. So yeah, 1 times half over 3 equals 1/6 area. And since the area of this is 1, the answer is just 1/6 over 1 equals 1/6, and that's the answer. So sometimes geometric probability in 3D can really help. Okay, anyway, next problem. So this one has to do with spheres. So oftentimes when there's spheres, they're like tangent. And if you know from like 2D geometry, when there's tangent spheres, you often want to draw their centers, and then the line through their centers will have a length that's equal to the sum of their two radii, and that happens in 3D geometry too. So yeah, let's try out that concept. So first of all, we have three spheres, and it's actually quite weird. Look, the radii have lengths 12 squared, 15 squared, and 20 squared, which is interesting. Oh, by the way, this problem's from 2021 CCA Math Bonanza, whatever that is. Okay, anyway, yeah, so we have three spheres that look something like this, even though this is definitely not to scale. Yeah. These two are like in front, and then there's also one in the back. But I'll just draw their centers. So their centers are these three dots. Don't worry about the circles for now, because I didn't draw the circles well, but the centers are those three dots, and the triangle right there is the triangle connecting their centers. And now I'll draw the feet of their altitudes to, not kind of bad. Yeah, the feet of their altitudes on the plane, or like the points at which they are tangent to the plane. So these red points. Okay. So now this problem, we basically just want to find the area of this red triangle, right? So I guess my first instinct would just be to try to find the side lengths of that triangle, because it doesn't look like a particularly nice triangle. It might just be like a random triangle, but we can always use Heron's formula on random triangles to find their areas. So let's try to find the side lengths of this triangle. First of all, let's look at the three pairs of circles at a time. So let's first look at the first pair of circles. It's white. So the first pair of circles are tangent. Wait, that was a tangent like this. And the ground is like that. And their centers are here. How about they have radii 144 and 225? Then the red segments, which are these, will have lengths 144 and 225. And then the length of this segment is the length of this like altitude from that one center to the other red radius. And you may like recognize this construction from 2D geometry. It's often used a lot to calculate the lengths of tangents. So anyway, now we can just use Pythagorean theorem on this skinny triangle. That was a very bad triangle. To find the length of this segment, which is what we want to know. Well, this one's just going to be 225 minus 144, and this one's going to be 225 plus 144. And now we just need to use the Pythagorean theorem. Well, it turns out that these numbers are nice for a reason. Of course, we could try evaluating what they are out, like 225 plus 144 is 369, etc. and this one is like 81, but it would be really time consuming calculating all of those sums and differences. So instead, let's just get right to it. So the unknown value is the square root of 225 plus 144 squared minus 225 minus 144 squared, which is, using difference of squares, the square root of their sum. Well, their sum is 2 times 225 times their difference, which is 2 times 144. And since 225 and 144 are squares, and in particular 15 squared and 12 squared, this is just 15 times 12 times 2. That's pretty cute. And guess what? It's the same for the other two. Like, maybe we just found like this edge of the red triangle, but the other two are calculated the exact same way. So now we know all the lengths of the red triangle. The lengths of the red triangle are 2 times 15 times 12, 2 times 15 times 20, and 2 times 12 times 20, using the same method that we used for that one. And by the way, 12, 15, and 20 were just the square roots of 144, 225, and 400. Okay, so now we've just got a triangle with side lengths 2 times 15 times 12, 2 times 15 times 20, and 2 times 12 times 20. They actually, well, actually, you might notice something else about 12, 15, 20. 12, 15, 20 is actually a right triangle. 12, 15, and 20. So maybe this triangle is actually a right triangle. Well, let's see. Maybe we can try like dividing out a factor. Well, yeah, like dividing out a factor and seeing if these three expressions are really in a 12, 15, 20 ratio. Okay. So, well, it would be very convenient. Let's just switch to different colors. Why not? So, it would be very convenient dividing out 12 times 15 times 20 to both, because to all of them, because they kind of all have that factor. So we would get 2 divided by 20, 2 divided by 12, and 2 divided by 15. Wait, okay. Okay, yeah. And I guess we could try also dividing out a factor of 2/5. We know 2. Wait. Yeah, we know 2. Wait, hold on. Okay, anyway, wait. 12. Oh, sorry. Wait, actually, no. I was being high. It's not 12, 15, 20. That's a right triangle. It's 12, 16, 20. But anyway, that's still fine because these lengths are still, these side lengths are still really nice lengths. So let's just evaluate them to like see what the numbers actually are. So 2 times 15 times 12 becomes 30 times 12, which is 360. 2 times 15 times 20 is 600. And 2 times 12 times 20 is 480. And if you divide out a factor of 120, divide out 120, you get 3, 4, and 5. So look, it is a right triangle, and it in fact is in the 3, 4, 5 ratio. And now to find the area of this triangle, we just find the area of a 3, 4, 5 triangle and then blow it up by a factor of 120. Well, 120 squared because it's area. So area, well, final area equals 120 squared times 6, because 6 is the area of a 3, 4, 5 triangle, which turns out to be 86400. And we're done. That was a kind of standard problem and a kind of standard solution. But yeah, this one is slightly less standard. Okay, so this is about like optimization. You have to figure out what the shortest path is. And where is this from? Oh yeah, I forgot exactly where this problem was from. I thought it might be from BMT 2021, but I couldn't remember exactly. I just remembered that this problem existed and it was a pretty good problem. So I think the hardest part of this problem is drawing it. So let's see if we can draw it. We have a 3 by 3 cube, which looks like this. But then there's holes in it, which makes it difficult. Okay. And then I guess I'll try to draw dotted lines. If this works, but it's very glitchy. Okay. Dotted lines are hard to draw. Anyway, yeah, there's like a hole in the middle of this space right here. Pretty hard to see. And then, yeah, this top face is also important. How about we say that the ant's initial vertex is here and the final vertex is here? Just to make things easy. Okay. And yeah, I think that should be about good. Okay, and then I will also need to draw some like lanes for like in the back. So I guess I'll attempt to draw this. We have like these squares in the back. Okay. Yeah. Oops, I already do those lines. Okay, and then there's like this one's a hole. So yeah. So it looks something like this. Yeah, it's pretty bad. Okay. I just need to like connect this so it doesn't look really weird hanging off of it. Wait, how do I like make this not? Yeah. Okay, anyway. Anyway, it looks something like that. Yeah, okay, this is really bad diagram, but anyway, so, okay, I'll just try to draw the important things. Okay, so anyway, the important thing here is to remember which like things are actually there and which aren't. So I guess I'll just color this in because I'll color in the cubes that actually exist. It's not like really hard to see anything, but yeah. So these exist, and this corner one exists. And then there is this one really important cube, and I'll let you know why it's really important in a second. So yeah, let me switch to a different color. This one cube right here, this is really messy. Anyway, this one cube right here is really important because the really important thing is that it's in the middle of the two vertices. So, like, what I mean by in the middle is, like, it's symmetric with respect to the final vertice and the initial vertice. Like, it's equidistant from the two, which means that basically we can just ignore half the path and assume that it will be identical to the other half. Like we can split the path into two halves and they will be the same. And like the place where we split them will be on this middle cube. And by the way, I'm talking about the optimal path. Like, of course, there's many paths, but yeah, we'll see that there's like one optimal path. So anyway, yeah, I'll color the rest of these squares red so that it's easier to see. I won't color all of them. Okay, so yeah, this one's red. And then this one in the middle here doesn't exist, but these two do. Okay. So first of all, like at first glance, where do you think the optimal path for the ant to go through would be? Like the ant basically has two choices. Either it could go like around like that way, or it could go in this hole right here, where like you kind of get a shortcut. Wait, I need to like make this red so that it will be more clear where the hole in the middle is. Yeah, now this is very red. Cute. But anyway, the hole's right there. So the second choice is to go through that hole and then back up like that. And like obviously, like the second path is better because like why would there even be a hole? First of all, why would there even be a hole if the first path is better? And also like since there's a hole, it like minimizes the distance you have to go because it's like a shortcut, you know? Okay, so oops, I just deleted that red stuff. So I probably have to quickly draw again. But anyway, so we know that we're going to have to go through the hole. Now the question is like exactly how we're going to do that. So I just need to draw these edges because these are very important. Okay, so do you see this edge back here that I'm outlining in green? It's like, it's not like the front one. Yeah, it's not the front edge. Like, like if this is the orange segment, it's not part of the orange segment. It's like back there. It's like the opposite edge of the yellow cube. So that edge is basically the edge that's in the middle of the starting point and the ending point. Which means that if the path is to be symmetric about the starting point and ending point, this midpoint of the green segment, which I'm going to color like purple, this midpoint, the ants will have to pass by that midpoint at a certain time. And we know that it's optimal for the ant to go this route because like the shortest route must be symmetric with respect to the 2 points, the starting point and the ending point. And if it's symmetric, it must be symmetric about this green edge, which means it must pass through the midpoint. So we have now simplified the problem a lot. We now have, like, there's only a small portion of the cube that we're now working with. We only have, yeah. So if you can see, I'll like circle it in white. We can like basically ignore the entire rest of the cube and only focus on this like top right corner. Basically, in particular, the distance from this purple point to the final point. And obviously, like the best thing to do in this kind of situations is to unfold the cube or cone or whatever you have, because it's much easier to visualize shortest distance when you have a 2D shape or a 2D map. So let's unwrap this and see what happens. Switching back to white. So first of all, we have that back face of the yellow cube. I'll actually draw it in yellow. We have this back face of the yellow cube, which has the purple point on it. I think the purple point is here. Okay. And then we have this red face right here. This red face that the yellow face is connected to. So I'll draw that in red. We have this face. And then next to that, it kind of like turns over a corner, and we have this face, which I will draw in red also. So we have this one, and then we have the last face, which contains the face with the ending point on it. So I'll draw that in red also. So if we unfold the map, we get this, and the final point is in white right there. So now all we have to do is draw the path from purple to white. Use orange. And that is the length of half of the shortest path. Of course, we have to multiply by 2 to find the entire length of the path. But now we've reduced it to one simple computation. So using the Pythagorean theorem, if we draw this one little square in, then this length is 3/2. Oops, that's hard to see. There we go. And the height is 3. So using the Pythagorean theorem, we get that length of the orange path is the square root of 3 squared plus 3/2 squared equals 3/2 times root 5. And multiplying that by 2, we get 3/5, which is the answer. Yeah. And so it's pretty hard to check that that's like the best possible answer, like if you're not 100% sure. But I guess you could always just try drawing out other paths and calculating their lengths, and eventually you'll find that 3/5 is the shortest. That's what I did, at least when I was doing this question. Anyway, okay. Moving on to another like plain geometry question with no combinatorics involved, just plain geometry. But this one's kind of difficult because it's 3D geometry and it's written in a very confusing way. So we have two cones basically. This is a very bad cone, but looks like this. And then we have another cone, and the keyword here is they intersect at right angles. So the fact that they intersect at right angles means that, okay, I'll draw this cone in red. It means that like their bases are at a right angle because their axes of symmetry intersect at right angles. So they must be positioned at right angles to each other. So yeah, we have this white cone and red cone intersecting. And then we have like a bunch of space that they intersect in. I'll have to do this in like highlighter. We have a bunch of space that they intersect in, like some space here. And then we have a sphere in that space. So like a sphere like this. And then we want to find the greatest value of the radius. Okay, so first of all, I mean, we could like write out the lengths that we know, because that's always a good thing to start with. So we know that this is 3, and this is 3, and this is 3, and this is 5, because 8 minus 3, and this is 3. Okay, but so to find the area of the sphere, basically the fact that it says maximum area of the sphere means that the sphere must be tangent to something. It doesn't say it explicitly, but in order to maximize the area of the sphere, you want to get it as big as possible, which means it must be like tangent to the walls of the cones. And so let's just say the best way to tackle 3D geometry problems like this is to look for good cross sections to take. So which cross sections might work? Well, obviously we have, so since we have like these cones at a right angle, it might be good to take a cross section that makes each cone look like a triangle. Because when you take the cross section of a cone, there's many different cross sections you can take. Like for example, you could take this one, which looks like a really weird shape, or you could take like this one. But the absolute best one to take is like the triangle that passes through the apex, because we actually know the dimensions of that triangle. We don't know the dimensions of these weird triangles. So we want to try to get a cross section that makes both cones look like triangles where their apexes are the top vertices of the triangle. And the best way to do that would be taking a cross section that passes through both of these lines. By the way, those lines are like basically the diameters of their bases. So like these lines. Now let's see what happens if we take those cross sections. So we had this one triangle, and then the second triangle, they're at a right angle, so their cross sections are at a right angle. Look something like this. And then, yeah, the centers are here. And then also notice that, so I'll draw the pink area again. The pink area ends up being like here. Now, in order for us to maximize the volume of the sphere or make it tangent to something, there's only, like the only things that it could possibly be tangent to are the edges of the cones. And if you think about a sphere and a cone, the only way for it to be tangent to the cone is for it to be like kind of tangent to an entire ring in the cone. Like if I draw a cone here, wait, not highlighted. Yeah. So if I draw a cone like this, and we want a sphere to be tangent to it, right? And also we want the sphere to be kind of like symmetric in the cone. Like we want the sphere to be right in the middle of the cone. We don't want it to be off to the side like this, because then the symmetry would not work and it could not be tangent to like both cones at once. So we want it to be tangent like this, which means that there's actually an entire belt of the cone, like an entire circle of the cone that is entirely tangent to the sphere, which means that if we take the cross section here, the sphere will end up being tangent to all the sides of the cones like this. And the reason why we know it's going to be tangent to all the sides is, I wonder if we can delete the pink stuff because that's annoying. Okay, there we go. And the reason why we know it can be tangent to all of this is because by symmetry, if this is the radius of the sphere, then this is also the radius of the sphere, since like this line bisects this angle at the top of the triangle. So we know that this is R and this is R. And then same thing here, if this is R, then this is also R. So there is a sphere that can be inscribed in the union of these two triangles, and that will be the greatest possible radius of the inscribed sphere. So now it's just a matter of calculating lengths. So let's see, what do we know? In red, we know that this is 3, this is also 3, and this is 5. And then the key thing is to notice this triangle right here. It's always nice to look for similar triangles, and this is a perfect example of similar triangles because we have this angle here, that is shared by both of these red right triangles, and we know the bigger one is in a ratio 3:8, which means the hypotenuse using the Pythagorean theorem must be the square root of 73. So then what do we want to find in this small triangle? We want to find the shortest side, which is the radius. And we know the longest side is 5. So drawing this off to the side, we have 5. And then, yeah, these two angles are equal. And then radius equals 5 times 3 over root 73 equals 15 over root 73. And then since the question asks for the square of the radius, the answer is just going to be 225 over 73, which yields an answer of 298. So yeah, this is definitely a pretty tricky problem, and it's not straightforward at all what to do, but taking the cross section definitely saves a lot of time, and I'm not sure, there is probably a solution where you don't take the cross section. It's just a lot more complicated and a lot harder to draw. So yeah, thanks for watching, and I hope you learned something about 3D geometry. See you next time.